these. We have electrocyclization, bring a poly that forms a ring. Then we have cycloaddition reactions, which are like the Diels-Alder, where two species come together and form a ring. Or we have this other category that we've not really seen before, at least not in this context, where you have a sigma bond that drags one of the substituent and moves somewhere. So these are the sigmatropic reactions, which just means sigma moving reactions. Okay, so in this case, it's this red sigma bond moves from this carbon atom to that one, which is this product. Now, these reactions are all conserved, okay, and they don't involve radicals, they involve neutral transition states, and they have stereochemical consequences that are a little bit hard to understand without looking at molecular orbitals. Now, one of the reasons that I like this area is because when students are first introduced to molecular orbitals, they seem, the whole concept seems a bit strange. We have this it's a mathematical construct that is supposed to explain chemical reactivity. We talk about bonding orbitals, but about non-bonding sigma and whatnot. And, you wonder, does this stuff have, does that predictive power? Well, I think you've seen that in some cases it does, but where you really see it is with paracyclic reactions. And so I mentioned that it was a good time to review how this molecular orbital business works, and just to make sure that we're all on the same page, that when you construct high molecular orbitals, you construct these from combining 2p atomic orbitals on each of the atoms, say of butadiene. So what I'm showing here are the 2p orbitals. Now when these combine, they combine to give, so 4 2p orbitals combine to give 4 molecular orbitals, shown here in order of increasing energy. Remember that the energy of the molecular orbitals correlates with the number of nodes. So 0 nodes is the lowest energy, and so on. For the purposes of this discussion, what we're going to be very interested in is the symmetry of the orbital. Now, when we talk about the symmetry, we're looking at the ends. So here, you'll notice that the shaded lobes of the 2p orbital are the same at both ends of the conjugated system. Remember what these colors mean. It means that the mathematical function which describes the probability of finding an electron changes sign. What does that mean? Well, it means that when you take the square of that function, there's no sign, there's no positive, and that's what gives you the probability. This is the square that gives you the probability. So we don't need to really think about what the mathematical, what the physical significance is. All we are interested in is the symmetry. So we notice that in this case, both ends are symmetrical here, anti-symmetrical, symmetrical, anti-symmetrical. So we have SA, SA. The other thing to remember is that substituents on the diene are not going to alter this picture. So whether we have butadiene, methyl, dimethyl, whatever, nothing changes. Once I put another double bond in conjugation, yes, then things change. So the symmetries of the orbitals, and in fact of what's known as the frontier orbitals. These are orbitals that are the highest energy and the lowest energy. The symmetries of those orbitals are going to determine the stereochemistry of these reactions, and we need to be able to predict that. Now, the example I gave you last time was this one, where I take a dimethyl cyclobutene, in this case, and I heat it up. And it turns out the equilibrium lies to the left for reasons that you can easily understand. That the cyclobutene itself is strained, and that the butadiene here, or if you will, it's a dimethyl butadiene, you can think of it as a hexadiene, is not. And when you have a trans orientation of the methyl groups on the 4-membered ring, you always get the E isomer. And conversely, when you heat the other isomer, the cis one, you don't get this. You get a different isomer. You get the cis trans one. And so it seems as if there is something that is controlling the reaction that is not completely obvious. I mean, there's, you know, without looking at orbital symmetries, there's no reason to expect any kind of selectivity out of this reaction at all, and yet it's completely selective. And so now we need to understand why. Now remember what I said about orbital symmetries. We're going to be looking at the frontier orbitals, which means we are going to be looking at the highest occupied molecular orbital not for the alkene, but always for the ring open compound. Okay, so this is a point to remember. When we're talking about these kinds of reactions, we always look at the ring open compound, okay, not the ring closed one, the ring open one. So we need to look at the symmetries of the butadiene. Now, we already did that, and I just showed it to you a second ago, but let's go back to it and take a look again. And so what we're going to want to determine is the symmetry of the highest occupied molecular orbital. Okay, so the highest occupied is antisymmetric. That means that the symmetry here and there are opposite. So red up, black down, black up, red down. A, antisymmetrical. Okay? So now let's apply that to the ring opening reaction and see whether we can make some sense out of it. So we're going to look at the highest occupied molecular orbital for the ring open compound. Okay, so here it is. And notice that it is antisymmetrical, that I have a red up, black down, black up, red down. Okay? Now, if I imagine grabbing the ends of this molecule, okay, grabbing it, twisting it in the same direction, in this case clockwise. Clockwise or counterclockwise isn't going to matter, okay, but whether it's, clockwise in one direction or counterclockwise, if they're both, it's not going to matter. However, they have to be rotating in the same direction, which means a conrotation. If I rotate them in this direction, then notice that black orbital here overlaps with black lobe here, overlaps with black lobe there, and you have a bonding interaction. That's a conrotation. They both rotate in the same direction. If they're rotated in the same direction the other way, that would be red on red, but it would still be a bonding interaction. On the other hand, if one of them rotates in one direction, and the other one in the opposite direction, it's a disrotation, then you end up with an antibond. And so it's that simple. And so you just look at the symmetries of the orbitals, the highest occupied molecular orbital. You determine whether the rotation at the end is in the same direction or in opposite directions. And then depending on whether that results in a bond or an antibond, you know which pathway is going to be lowest in energy. Now, this is the simplest way of doing it, and it gives you the right answer. And I mean, it's the correct way of doing it. I haven't fluffed anything. If you were to look at Woodward and Kaufman's 1960s paper, they go through a much more complicated argument that correlates the high molecular orbitals in the starting material with the product. And you can do that. We're not going to do that because it's more work than you need to do to understand what's going on. You can do that. You'll end up with exactly the same result in every case. And so the way I'm going to teach you how to do this is correct and it's simple. Okay, so just so you know, some of you have the curiosity to go back and look at that work and maybe a little bit puzzled. It's not going to look quite like this, but it gives you exactly the same result. So let's go over that again. So you have a cyclobutene that has some stereochemistry, and you want to know when you ring open this compound, because the equilibrium lies towards the ring open compound. You know, what do you get? EE, you get EZ, what do you get? And the way you know that is by determining whether that ring opening is, or ring closure, same thing, is a con or disrotation. Conrotation, exactly what it sounds like. Both rotate in the same direction. Disrotation, exactly what it sounds like. Rotate in opposite directions. One of these rotations results in a bond. Overlap of the same sign of orbitals. The other, in an antibond. And so this is the low energy pathway. Now, the low energy pathway, why? Well, because as you proceed along the reaction coordinate, it's the pathway that allows you to maintain bonding throughout. Okay, so you don't end up having to completely break a bond, make a bond. Okay, that's why it's lower in energy. It's a lower energy pathway. So in this case, it is the symmetry of the highest occupied molecular orbital, or if you will, the phases of the n carbon orbitals that determine this. Okay, so a very simple concept. Now, this is why this is so important. You know, you have, just imagine before anybody knew about this stuff, they had this huge body of data, you know, and, you know, some things gave this kind of stereochemistry, some things gave the other. Nobody understood why, and so, as I said, they called these no mechanism reactions. And then somebody came up with an idea that actually took all this disparate information and organized it in a way that made sense. And so that's the kind of thing that we like to see in science. Okay, now, the example that we showed was for a diene, okay? Now, when you put a triene, you can still get electrocyclizations. In fact, on the first page, I had showed you an electrocyclization here. But what I didn't show you was whether this is a con-rotation or a dis-rotation. Here it doesn't matter, because whether it's con or dis, you end up with the same product because you don't have substituents in both CH2 and CH2, so no stereochemistry there. So there's no way to know. However, there are rules that will tell us whether it's a con or a dis. And here's how you do it. For the diene, the highest occupied molecular orbital is antisymmetrical, right? Because it goes symmetrical, antisymmetrical. So second molecular orbital is the HOMO for the diene. If you have a triene, you have 2 more electrons, and so you have a third molecular orbital. So that goes symmetrical, antisymmetrical, and then the third one is going to be symmetrical again. And so for the diene, for the triene, the HOMO is S. Because it is S, then the same process that I showed you is going to give you a bond when it involves a disrotation. Okay. And so you can generalize. This is completely general, which is nice too. If you have 4 n pi electrons, it's going to be a con-rotation, 4n plus 2 dis. Don't try to memorize that. There's no reason to. Okay? So it gets a little more complicated as we consider not just thermal reactions, which is what we've done now, but when we consider also photochemical reactions. So there are 2 ways to activate these kinds of processes. One is by heating them up. That's a thermal reaction. The other is by shining UV light on them at a wavelength that matches the HOMO-LUMO gap. Excuse me, that's the photochemical process. So remember that what we just said is for the thermal reaction. Okay. Now we go to the photochemical reaction. Let's think about butadiene again and the orbitals that we had for butadiene. Okay? And okay, so here's butadiene, and let's imagine that I take butadiene and I shine light on it. And the light that I shine exactly matches the energy gap, the wavelength of the light, or the frequency, if you will, because those are related to the energy, exactly matches the difference in energy between the HOMO and the LUMO. Then what happens is one of these electrons from the HOMO absorbs that energy and jumps into the LUMO. And so at that point, I don't have ground state or the lowest energetic state of butadiene. I have what's known as an electronically excited state. Okay, now this is very common in nature. Actually, a lot of reactions in nature are photochemical reactions. Tell me one. There you go. Yeah. So photosynthesis. Yeah. So they all depend on exactly this kind of process to get going. And so when you do that, of course, you alter the electronic distribution in the molecule, And so bond lengths and angles can change, okay? But we don't need to think about that right now. However, in the electronically excited state, this becomes the HOMO, right? Because this will be the highest occupied molecular orbital. So, here we go. So, because the excited state has the opposite symmetry, the excited state and the HOMO in the excited state has the opposite symmetry as the HOMO in the ground state, then the rules just switch, right? So the highest occupied molecular orbital in ground state butadiene was what? Was antisymmetrical. Go up one to pi 3 star, and that's going to be S, going to be symmetrical again. And so if the ground state was a con rotation, then the excited state has to be a dis rotation. So in other words, if I say con dis for thermal, if I put photochemical here, these are just going to switch to dis con. And the reason is just because the symmetry switches as soon as you go up one more level. It is just amazingly simple. This just means that, so here it is. So the photochemical one just has these two switched. The reason? Well, because the symmetry of the HOMO is changed. That's it. Now, let's take a look at hexatriene, okay? And let's look at the photochemically excited state of hexatriene. Now, see if I can, let's show this first, okay? Let's show this. So I'm not showing all the orbitals for hexatriene because I don't have to, right? Although the only ones I'm interested in are the frontier orbitals. Easy. So 2 electrons in pi 1, 2 electrons in pi 2, 2 electrons in pi 3 in the ground state of hexatriene. Pi 4 star is the first antibonding orbital, and then there's a pi 5 star and pi 6 star, right? But we don't care about those. So all the action is going to be right here. So you know that this is S, right? Because the lowest energy molecular orbital has no nodes. So it always is going to be S. And the next one will have 1 node, so it's going to be antisymmetrical, symmetrical, antisymmetrical. So in the excited state, the photochemically excited state of hexatriene, pi 4 star is the LUMO. That is antisymmetrical. So I've drawn in all the orbitals here for pi 4 star. But you know what? I didn't have to because here is where it matters. And so a con rotation here results in a bond. And so for a 6 pi electron system, the photochemical reaction is a con rotation. Don't memorize it. You don't need to. Okay? So the way, how do I keep this stuff straight? Here's how I keep it straight. Very simple. I just remember that the thermal reaction, so here I'll just show you how I do it. So 4 pi, I know that thermal, that's delta, is going to be a con rotation. I just remember that, right? Just something I know. I know everything else from there because I know that the photochemical will be this, and then for 4n plus 2 pi systems, it's just going to be opposite. It's going to be this and con. And so I can figure it all out just by remembering that. And don't copy that, as I said, you don't need to. So very simple for for correlating all this data. Now, one thing you have to remember is that what we're talking, the way I've introduced this topic is as a cyclization. Okay? So in this case that I have on the board, left to right. But because of microscopic reversibility, anything that I say about the ring closing reaction has to be true for the ring opening reaction too. And what the rules, these rules that we're talking about this con and all that tells you nothing about the equilibrium, okay? The equilibrium is determined by the energetics in each case. So, for example, for the 4-membered ring, the energetics favor the ring open one. For some 6-membered rings, if they're strained or whatever, if you build something in, you may have an equilibrium that favors the ring open compound. So the position of the equilibrium, we're not talking about. All we're talking about is the stereochemistry going from one to the other, okay? And so the pathway is what we're talking about. A low energy pathway with a concerted process that converts one to the other. Okay, so let's take a look at how that works in this case. So the two methyl groups are on opposite sides. Remember that this is going to be a 6 pi electron system. Why 6 pi electron? Well, because we always count the pi electrons in the ring open compound, the ring open one. So 2, 4, 6. Now, if I go back to my rules that I had, 6 electrons is 4n plus 2. I said that this was what? Thermal. So 4n plus 2 thermal, this better be a disrotation. And in fact, it is. You can do the molecular orbital picture, and you can see that it is. So that tells me that when I do a disrotation, I end up with the EZ isomer. And I don't get EE or ZZ, only one. Okay? Now, there'd be absolutely no way to make that prediction without orbital symmetry. I mean, if you didn't know any of this stuff, and someone says, well, I keep this up and it opens to triene, you would have no clue about the geometry at the end, okay? And so the very nice thing about this stuff is that the rules are ironclad, okay? Woodward and Hoffman in their seminal review on this material, they actually say something that you'll never see again in a scientific paper. They say there are no exceptions. I mean, that really takes some brass to say that, but you know, actually there aren't any. And except, okay, no, it's not. It's actually not an exception. But here, let me tell you why you need to be careful when you hear that. So let's just say that I do take a. Doesn't matter whether I'm talking about a ring closure or ring opening reaction. And I perform the reaction, and I go to the NMR machine, and I take the spectrum of the product, and I determine that, oops, it's not what the Woodward-Hoffman rules predicted. What that tells you is that you didn't have a concerted process. What that tells you is that it tells you one of two things. Either that the reaction was not concerted. How could it not be concerted? Easy. Goes to a radical. Or it isomerized. Okay, so he was right. There are no exceptions. But you have to be very, very careful how you interpret your experimental results. So anytime anybody thought there was an exception, it turned out, no, actually there was a radical involved or something else. So I think he's on, or was, since he's no longer with us, on firm ground writing that. As I said, in a scientific paper, you will never see something quite that bold. Okay, so this pretty much covers what I've been saying. So the selection rules just means 4 pi on this, whatever. Those rules only tell us which of the processes will be faster. So it addresses the kinetics, tells you nothing of the position of equilibrium. That's determined by each case by the relative energies. So what we're talking about is kinetic, the kinetics, not the thermodynamics of the reaction. Thermal reactions, you inevitably get thermodynamic control. Well, because you're heating it up and you end up setting up an equilibrium. And so with the photochemical reactions, however, you don't. Because photochemical reactions are performed typically at low temperature. Now, the photochemistry gives you a kind of a handle on something that you may not think about. Okay, so making this cycloheptadiene is not all that hard to do. And because it's a small ring, the geometry of these two alkenes is always going to be Z, okay, Z and Z. You're not going to get a trans double bond in a 7-membered ring. If you do, it's going to be extremely reactive. It's not going to have much of a lifetime. So this is a 4 pi electron system, and if you shine light on it, then 4 pi photochemical is this rotatory right? So in the distro, just imagine grabbing those two hydrogens and pulling them up. So if I look at the molecule from this direction, put my eyeball here, then on the left-hand side, it's going to look like a counterclockwise rotation. On the right-hand side, it's going to look like a clockwise rotation. I'm going to end up with this as my product. Okay, so imagine looking at it down this way. So your eye is where the pen cap is. To get this kind of geometry, on the top side, it's going to have to swing that way. So that's going to be counterclockwise here. It's going to be clockwise. But in any case, it's disrotatory. And you get 42% as it turns out of this compound. Now, this process works for a very simple reason. And that is that the diene absorbs the UV, but the alkene does not. Okay, now let's think about that. When we talked about UV spectroscopy way back when, what did we say about the length of the conjugated system and the wavelength of absorption? Does anybody remember? This is kind of a fundamental thing that's going to come up again if you take quantum chemistry. So you end up with, so you can have 1, 2, you can have 2, 3, 4, 5, I don't know how many conjugated double bonds. And if I compare the lambda max for 3, 4, 5, 6, 7, n double bonds, what happens to lambda max as it gets longer, longer, longer? Remember beta carotene? The first part of it?
It covers a longer range of frequency.
No. So the lambda max is the lambda max for each one of these compounds, right? So as the length of the chromophore increases, the lambda max becomes longer and longer. Okay, so that means that the energy gaps become smaller and smaller and smaller. So what that means is that dienes will absorb energy that is less, will absorb light that is has less energy than what you need to excite the alkene. So when we run UV spectra, remember that we don't see alkenes because they're at much shorter wavelength than what we're looking at. And remember that as I string together enough alkenes, then all of a sudden the compounds absorb the visible. That was the beta carotene example. So if you get enough of those double bonds conjugated, then you have something that's orange, and you can see it with your own eyes. You can see the absorption. Okay. So back to this. Here I have 2 conjugated double bonds. Here there's only 1 double bond. This will absorb the light, that won't. And so once you go from here to there, it's trapped. Why? Because you can shine the same UV, the same light at the wavelength that this absorbs. This will never absorb it because why? Because that light doesn't have enough energy. And so it goes in this direction, and it is a unidirectional reaction. You don't have to worry about it. Now, why is that important? Because look at what you've done here. You've gone from something that doesn't have strain to something that's got a lot of strain. If this were a thermal reaction, no way. The equilibrium would always favor the less strained compound. And so photochemically, you have this tool, right? This is a very important thing to be able to do. You can actually trap things that are higher in energy. So it's a neat trick because thermally, this is going to open up. Now, let's think about how it would open up. When this opens up, so let's say I heat this. Okay, let's do the thought experiment. Let's say I heat that. So it's a cyclobutene. What's it going to give me? If I heat a cyclobutene, what's it going to give me? It's right here, guys. It's going to give you a diene, right? Okay? Good. And if I heat it, and it gives me a diene, then is it going to give me the same diene? So if I heat this up, let's go back to here. No, it doesn't. Why is that? Yeah, because it's going to be a conrotation. This is a disrotatory closure, and so the ring opening to give this would have to be a disrotation. But that won't happen thermally because of the selection rules. So if this opens, it's going to have to be by not a disrotation, but a conrotation, which means it's going to give me something that is super strained because I'm going to have one trans double bond, and you guessed it, one cis double bond. And so that process is going to be nasty. This is not going to sit around. So you can heat that thing up, but you can be sure that one of two things are going to happen. Either it's going to go via a radical pathway, because this is too strained, which is the likely thing, or if somehow it gets over the hump and it gives you this is going to react, and you're never going to see this because this is way, way too reactive. And so the pi electron count always refers to ring open compound, okay? So when we talk about opening this thing, we're not talking about 2 pi electrons, we're talking about 4, and so that's going to be a conrotation when it's thermal. So what this all means is that you can sometimes trap very energetic molecules that have no concerted pathway for ring opening. They always can undergo radical reactions. You put enough energy in there, and you bias the molecule to undergo a homolytic cleavage. So it can always do a homolytic cleavage, give you a diradical, and react via the diradical. That can always happen. But if that doesn't happen, then you can trap things like this. This is duobenzene. Remember, this was one of the structures that had been proposed for benzene before people knew the correct structure. Well, it turns out you can make duobenzene, but for the reason that we just articulated up here, thermally, this isn't going to do a concerted reaction. So you can actually isolate these things with all their strain. So that was pretty much what we needed to talk about with respect to electrocyclizations. But remember that we had other paracyclic reactions. What is a paracyclic reaction? Just means electrons moving around the ring. And so the reactions we talked about were these. Now what we're going to talk about are cycloadditions, and we're going to go back to our favorite one, which is always the Diels-Alder cycloaddition. And so that when we talked about the Diels-Alder, we didn't really explain too much because it wasn't, we didn't have to. So now let's take a closer look at the Diels-Alder and see how it fits into a much larger body of cycloaddition reactions. So the Diels-Alder is not the only cycloaddition out there. There are lots and lots of them. Some of them work one way, some work another, and you guessed it, we can predict based on frontier molecular orbitals. So, first of all, how we count. And the cycloaddition reactions are always going to be classified according to the number of pi electrons participating. And how do we know how many pi electrons are participating? Well, just count the double bonds in this case. So, here you have 2 double bonds, 2 times 2, 4, 1 double bond participating. You say, but there's a CO double bond, but the CO double bond doesn't participate. Okay, so participating double bond is here. So only 2 electrons here, 4 electrons there. So this is a 4 plus 2. That's the Diels-Alder reaction. And if I have 2 alkenes, then it's going to be a 2 plus 2. And of course here you get a 4-membered ring, whereas here we get a 6. So the 2 plus 2 tells you that it's going to be a 4-membered ring in your product. A 4 plus 2 tells you it's going to be the Diels-Alder 6-membered ring. Okay. So this is just a classification. It doesn't tell us anything about stereochemistry. It doesn't tell us anything at all. It's just classified by the number of electrons. However, there is another classification that we need to think about when we talk about cycloadditions, and that is the plane of each reacting molecule. Gee, what does that mean? Well, okay, so here we go back to, I guess, the early beginnings when we talk about stereochemistry, right? And so we need to have in our minds a picture that we can refer to of the shape of the molecule. Okay, so whenever you look at a molecule, you need to be able to kind of visualize. You can't do it in your head, you build a model, that's perfectly acceptable. The molecule is really, really complicated, and you can't build a mechanical model. You can go to your computer and build a 3D model these days, and that sometimes helps. But it is very important to be able to visualize the three-dimensionality of these molecules. Why is that? Is it because, because we like to? No, it's because the structure and the reactivity are always closely related. Okay, so structure reactivity are sort of opposite sides at the same point. And so if you know something about the structure, you know something about the reactivity and vice versa. So that's why structure is important. So back to here. We classify these reactions according to the plane of each reacting molecule. Now, I'm going to introduce some geek speak here. And we don't really need to, don't obsess with the terminology, but understand the concept. So just think about it this way. Let's just say that you have two molecules, and they're coming together to form bonds. Okay. Now you think of, and we're talking about pi bonds here, okay? So the pi bonds in any molecule, you have two planes, right? So let's just start with the simplest pi bond we know, okay? Which is the one in ethylene. I'm showing the sigma bonds here, I know that. But think about the two pi molecular orbitals, right? So I'm going to shade one dark and one light. And we know that we have electron density that lies in a cloud on the top face of this molecule, and we have electron density that lies on the bottom face of this molecule. Okay, so those are the bonding pi molecular orbitals. Okay, so now think of this coming together with another molecule. Okay, to form a ring. And so the bond's going to take place on the same side of the molecule. So one bond from here, one bond from there. Or you can have a different situation where this molecule comes together with another molecule to form a ring. One bond forms this way, but one forms from the other face. Okay, that could happen too. Those are the only two possibilities. You say, yeah, but they can both come from the top. Yeah, but that's the same as two from the bottom. So this would be called anterafacial, which means just opposite faces. And if they come from the same face, it's going to be called suprafacial. Okay? So that's what the supra and para means. Now, when we look at cycloaddition reactions, we need to think about not just how many pi electrons, but suprafacial and parafacial addition. Okay, so this is just what I illustrated for you. Now let's see how this works in the context of the Diels-Alder cycloaddition. Okay, now I'm not showing the phases of the orbitals because I don't want to tell you if it's the HOMO or the LUMO or whatever. That's going to come later. But let's just look at the pi molecular orbitals, and I've shown these as individual 2p atomic orbitals for butadiene and an alkene. And so if I form the bonds here as shown, then it's the same face of the dienophile. It's the same face of the diene. So this would be a suprafacial addition because it is same face of the diene, same face of the dienophile. Still 4 + 2. And so the way you would show this, the way you would indicate this is not just 4 + 2, but 4 subscript s plus 2 subscript s, saying that suprafacial with respect to the diene, 4 pi electron, and superfacial with respect to the pi. Okay, so it's a suprafacial cycloaddition. Now that's one possibility, but there's another one. The other one is that it's superfacial with respect to one partner and parafacial with respect to the other. Now what would that look like? Well, for the Diels-Alder reaction, it would look like this. This would be a 2 suprafacial, same situation that we had above, right? Your bonds, both bonds forming from the top face, as I've shown it, both bonds forming from the top face. So it's 2s here, 2s there, 2s. But look what happens. This side bonds the bottom face, this side bonds the top face. Bottom, top, bottom, top. So for the 4 pi and parafacial. So that would be the difference. There's a third possibility here too, right? And that would be 4s 2a. And that would just be a little bit different. So we have, now for the 4 plus 2, you've got 3 different reaction stereochemistries really to consider. And so, of course, you can tell that this is going to make a difference, isn't it? Because depending on which orbitals I'm looking at, which symmetries I'm looking at, this kind of overlap may be bonding or anti-bonding. And if this is bonding, then this one is anti-bonding and vice versa. So we have to have some kind of rule that takes into account this suprafaciality or anterofaciality of the reaction, because things are going to change. So the selection rules for the cycle additions have an added level of complexity. That added level of complexity is supra, antera, antera, supra. Okay? And so now it gets a little bit complicated. Okay, so to recap what I just said, the alternative cycle addition, and by the way, this is how the Diels-Alder takes place, just so you remember. It is supra-supra. We'll see why. But the alternative cycle addition geometry would be not same face, but same face, different face. Now, in order for that to happen, what you'd have to do is you have to twist one of the molecules a little bit. Because this kind of interfacial overlap will only happen if I take the dienophile and twist it a little bit. I'm just going to move it over, then I can get that kind of overlap. Okay, so there has to be something that biases the reaction one way or the other. Now, what do we look at? For the electrocyclizations, the ones that we talked about before this cycle addition business, all we had to look at was the highest occupied molecular orbital. Here, for the cycle additions, we're going to talk about the highest occupied of one partner and the lowest unoccupied of the other. So we're going to look at a homo-lumo interaction. So you say, well, which one is there going to be the homo and which one is the lumo? This is nice, doesn't matter. Doesn't matter which one you pick to look for the homo or in which one you pick for the lumo. The outcome, the stereochemical outcome, is always going to be the same. So you can pick homo of one, lumo of the other, or lumo of one, homo of the other. Same. Now, having said that, of course, the symmetries are going to have to be matched at the bond-forming ends of the molecule. So remember, for the Diels-Alder reaction, you're forming 2 sigma bonds. For each one of those sigma bonds, the overlap has to be bonding. Okay, so you can't have a bond and an anti-bond. That's going to be high energy. It's going to be a bond and a bond. And so, in order for the addition to take place in a concerted and manner that has a low activation energy, that's what we mean by this. The symmetries of the homo of one component, doesn't matter which one, and the lumo of the other component, doesn't matter which one, but it has to be the opposite one, must be matched. And so homo-lumo or lumo-homo have to match. It doesn't matter. If one matches, the other one will. Okay? So here's how you think about it. You think about the homo as being analogous to the valence electrons of an atom. Okay? So these are the highest energy electrons in the molecule. So any kind of bonding that takes place isn't going to take place from the low energy electrons. It's going to take place from the highest energy ones. Because why? Well, because you don't have to pump as much energy into the molecule to do anything, because they're already high in energy, right? For the same reason that the valence electrons are where all the action is. These electrons have to go somewhere. Remember, electrons don't just go anywhere they want. They have to live. They always live in orbitals. So if I'm thinking about the highest occupied molecular orbital in one molecule, and those electrons going into some other reacting molecule, they're going to have to go into an orbital in that other reacting molecule. They can't go into an occupied molecular orbital because you can only pump 2 electrons per orbital. So there's only one place they can go, and that's an unoccupied molecular orbital, empty one. So that's why they'll go, you can think of them as flowing from HOMO to LUMO. So it makes physical sense. And so it doesn't matter whether you pick the HOMO of the diene, LUMO of the alkene, or vice versa. Conclusions will always be the same. So let's just take the highest occupied molecular orbital of the diene. Now the diene is butadiene here, and so the highest occupied is antisymmetrical, as we've seen. It's antisymmetrical. The LUMO, the lowest unoccupied of the alkene, is also antisymmetrical. Right? Because the symmetrical one would have had red, red, black, black, and here you can see there's a node in the middle. If I bring these together suprafacially, same side of the diene, same side of the dienophile, red overlaps with red, black overlaps with black, and we're happy because we have bonding interactions at both ends. Okay? That's because it was SS. So the match is achieved here for 4s, 2s. But of course, you being smart can tell me that, oh, but, there's another way we can do that too. What is it? 4a, 2a. Yeah, very good. So 4a, 2a would also work, wouldn't it? Because then I would be looking at anterafacial here, anterafacial there, and yes, that works too. But the Diels-Alder reaction doesn't go 4a, 2a. No one's ever seen one of those. It only goes 4s, 2s. Why? Yeah, it's just too strained. The transition state for 4a, 2a has way, way more strain than this one. So there's a low energy alternative. So that brings us to a point, right? There's nothing inherently wrong in terms of orbital symmetry with the 4a plus 2a, but there's something definitely wrong thermodynamically. And so we're not looking at, with this, we're not looking at the thermodynamics, we're just looking at the kinetics. And so that doesn't mean that you abandon your common sense. You recognize that the 4a, 2a has strain. So yeah, that's right. Now, this as I said, conforms to what we've seen for the Diels-Alder reaction. You'll recall that when we did this Diels-Alder reaction, we had these two groups being cis, and these two groups being cis. And we said that this was the rule. That is, now you can understand why. That happens because you have a conserved reaction, number one, and because that conserved reaction is actually 4s plus 2s. If it were 4a plus 2a, you wouldn't get that. Okay? So yeah, so it makes sense. Now, what about the 2 plus 2? Now, 2 plus 2 is kind of a strange process, but it's an important one, and I'll remind you why. Thermally, it doesn't work. And why doesn't it work? Well, because if I look at the HOMO-LUMO, then here's the highest occupied molecular orbital of ethylene, and here's the lowest unoccupied, same as we saw before. And here I get bonding, but here I don't. This is anti-bonding. Bonding, anti-bonding. So 2s plus 2s is not going to work. No way. Can't happen. But we've seen 2 plus 2s. Well, this is thermal. What about 2a plus 2s, right? You just told me correctly that the Diels-Alder had another option. Look, this one has another option too. Why can't we just have these two overlap, and then this one overlaps with that. So it would be a suprafacial, anterafacial. 2a, 2s. Orbital symmetry matches. What's the problem? Well, it's the same one you told me. It's just too strained. So with two ethylenes, sure, the orbital symmetries match for 2s plus 2a, but you just can't twist them enough. Now, if you had something other than ethylene, if you had a longer bond and a shorter bond, so not carbon, 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 then you can sometimes see this 2s plus 2a. But with carbon, no, because it's just too strained. So the orbital symmetries, sure, they work for this. The trouble is, you can't get to that transition state because it's strained. Okay, we'll pick up on Monday. Remember, Saturday, tomorrow, 11 a.m.